Again, I will double check. Done. Okay, so we have this basketball, and let me just quickly also revise where were we last time. What I was, yes, sorry.
PSIG. What is PSIG?
PSIG. I will tell you. Just basketball. Yeah, pound per square inch. And G, I mean gauge pressure. But remember that in an exam setting, I will not be informing you this. You should know that we are talking about gauge pressure by default usually. Let me answer your question in a better way. Yeah, gauge pressure. You were in the pressure vessel class, right? Pressure vessels when we started, just out of curiosity. Pressure vessels.
Last week.
No, you were there.
I joined online.
You were online. What about Ahmed? You were not? Okay, you were not. So just let me tell you a couple of formulas and then you can join us. Number one, very quickly, there is something called circumferential stresses.
We're going to talk about the PR.
Let me tell him. Cylindrical thin vessel, okay? Coca-Cola can. Just remember Coca-Cola can when we are talking about all of this. So I'm talking about a Coca-Cola can. So we have circumferential stresses, which is known as hoop stresses. You see Coca-Cola can, look at it, and you have circumferences like this, right? This is circumference. So this is what is known as circumferential stresses. Stresses that are along the circumference.
We're going to call them
hoop stress. Yeah, but circumference is a word that you know better than hoop.
Are they shear stresses?
No, they are not shear stresses. Good question. We are talking about normal stresses.
Normal stresses acts on the circumference of the object.
Yes, in a circumferential direction. So you will have to go through the last lecture to understand it completely. But my point is, I'm talking about normal stress. Good question, because I use the sigma.
I think normal stress is more of the longitudinal stress.
No, wherever I use the symbol sigma, that is a normal stress. So he's right. We are not talking about shear stresses. Now I will answer the second question. Then I talked about that for cylindrical thin vessel, there is what is known as longitudinal stress. So in a Coca-Cola can, look at its thin surface. Now I'm talking about longitudinal. Longitudinal means axial. Again, that's a normal stress. Normal stress means sigma. So both of them are normal stresses. So again, let me revise quickly. I'm talking about thin pressure vessel. I'm talking about cylindrical pressure vessel. Imagine a Coca-Cola can, which is pressurized. It has pressure inside it. It has a thin wall. Number three, I'm talking about the normal stresses. I'm talking about hoop stress, which is circumferential stress, the sigma one, it's PR over T. The other one is the longitudinal or axial stress along its wall. This is known as sigma 2. These are principal stresses. That's why I use the word 1 and 2. Now that you have joined us, I think now you are good to go with us. Now, remember that in the same class, I ended the lecture by saying that if you have a spherical,
it's the same as
thin pressure vessel, write the word pressure in both of them. The stress will be stress 1 equal to stress 2 equal to PR over 2T. Done? Now, if you understand this, I think now you can join us. So today's example, I have to finish this topic, by the way, gentlemen. What happened? Today's example is very good. The question says you have a basketball. The ultimate tensile stress of the material of the basketball is 2000 pounds per square inch. There is one more comment so that you join us. The pressures I'm talking about in all of this are gauge pressures. This is another thing that I explained to the class. So for example, if I tell you, okay, again, Coca-Cola can is not a very practical system in terms of do we really care about Coca-Cola can, but something we understand. So if I have a Coca-Cola can, if I tell you its pressure is this, actually I am talking about Coca-Cola's can's gauge pressure, because at the end of the day, its exterior is also subjected to an atmospheric pressure. So what I care about when I shake the can is the pressure that is sitting inside, the gauge pressure, So I'm talking about its pressure inside relative to the environment. You have gone through the fluid mechanics. I know you understand the gauge pressure. Acha. So just finish the question. If it's sphere, I have told you that the formulas are PR over 2T. The question says that you have to tell me what are the, oh come on, what is even the question? Yeah, what are the stresses inside this? So it gives me pressure is 9 pound per square inch. Is it visible? Okay. Multiply by what is the radius? I think radius will be 9.5.
So these are the stresses within a basketball, inside the basketball.
These are the stresses in the material of the basketball. Oh, for sure.
By the pressure inside air.
Yeah, there is a pressure inside. There is a pressure inside basketball. When I'm talking about the stresses, I'm talking about the stresses in its wall. In a Coca-Cola can, when I'm talking about stresses, I'm talking about the stresses in its thin wall. Inside it, there is pressure. I'm not going to talk about some stresses in some hollow environment. Like what is the stress here? Nothing. It's pressure. What is the stress here because of air? That matters to me. So good question by Hussain. 9.5 divided by 2 minus 0.125. Do the number crunching and we will proceed to next example. 4.625 divided by 2 into T. Now, just for the students who have joined this class, remember that for a thin pressure vessel, there was a criteria I also told the class.
R over T has to be larger than 10.
R over T, where R is the, you have to, in a, what was R? Was it inner radius? R over T has to be greater than 10 for us to qualify a cylinder as thin. So for example, how on earth would I know that Coca-Cola can is a thin cylinder or it's a thick cylinder? I have to see the R. Again, I am using in this class R as the inner radius. It's not a big deal. Probably in some other books, you might see that someone is telling R as the mean radius, whatever. I am saying that inner radius is R, T is the thickness. Do the R over T and double check whether that is greater than 10 or not. There is a 90% probability that in an exam, if I give you the question, of course, I would love to give you a thin pressure vessel. Otherwise, if I end up giving you thick pressure vessel, then you will not be able to solve it. So R over T for this problem is greater than 10. Double check yourself. I'm not going to do it for you.
Why did you divide 9.5 by 2?
I am trying to find the inner radius. And the outer dia is 9.5. Yes. So it comes out to be 167 pound per square inch. Now in this pound per square inch, you are not going to put G or A. That's ludicrous. That's ridiculous. We don't put these absolute or G in stresses. We talk about pressures. We qualify them as absolute or gauge. Now, honestly, I'm also now struggling to realize why did I even give you ultimate stress? What was the question? And what did I end up doing? Anyways, we have ended up finding the stresses inside this. Apparently, it will not burst. That's fine. Because the ultimate stress that is given to us is 2000 pound per square inch. If in case you are wondering, why did you give us sigma ut and why did not you give us yielding? The answer is that basketball will burst. It will not yield. If I keep on giving it more and more pressure, boom, it will just burst. So I doubt that you really would have any yielding. It will just burst. That's why I gave you ultimate stress value. And our stresses are telling us that basketball is good to go actually. So I went at sonic speeds in case you arrived late. Let me go over for a thin cylinder pressure vessel. I talked about sigma 1. Hang on. So sigma 1 is a hoop stress, right? Circumferential stress. So move your hand like this. That's the hoop stress. Circumferential along the circumference of that thin wall. We had a discussion at the end, so that's why I thought that I should be specific. Hoop means circumferential. Longitudinal means along the length of along the axis of the Coca-Cola can wall. Then for spherical, our values, our stress 1, that is the circumferential, and stress 2, that is the longitudinal. Both of them are PR over 2T. 6, 5, 4, 3, 2, 1. Should I go? Okay. Yes. No. Take your time. Even you can take your time. Relax. Yeah, it is a pretty easy topic, but few things that you have to realize. Remember that why am I using stress 1 and stress 2? Because interestingly, these are also the principal stresses. So remember this thing. I could have used sigma subscript hoop. I am allowed to, but I chose 1 because interestingly, these are principal stresses as well. Both of, yeah.
In P, what is G? 9 psi G.
Gauge pressure.
Gauge pressure.
Gauge pressure. Inside basketball, if I'm telling you there is a pressure of 9 pounds per square inch, I'm telling you the gauge pressure. So absolute pressure is of air is 100 kilopascal. Let me convert it for you in English. 14.7 pound per square inch. When you have 9 pound per square inch gauge, that means inside the basketball, actually there is a pressure of 9 plus 14.7, which is equal to something. I'm not sure what kind of system is being used here in Cyprus. I haven't driven a car here, but when you go to a gas station here and you ask them to fill even air in the tires, back in Pakistan, what we say is, please fill in 28. So what is that 28? We ask the person to fill in 28 pound per square inch pressure of air inside our tires. But what is that 28 pound per square inch? That's a gauge pressure. So actually the guy is filling 28 plus 14.7. Okay, gentlemen, yes.
Also, in previous question, you said that sigma 1 and sigma 2, right? So
Always, even the derivation, I use sigma 1 and sigma 2.
Yeah. Could you scroll previously? Yeah. So when we say sigma 1 and sigma 2, we are talking about the spherical, right? So it's like, yeah, when we dividing into a square segment, yeah, for example, like this ones. So sigma 1 will be upward and sigma 2 will be in x direction, right? So we're thinking like that.
So it's like a ball like this. Sigma 1, if this is the ball, sigma 1 will be like this along the surface, and the other sigma will be 90 degree to it. Both of them are 90 degree to each other. In the derivation, I made this diagram, I made a cut and I showed all of you this. But anyways, now do this problem quickly and I have to finish this topic. The problem says that now I have this tank. Now you have to understand these formulas. Whenever you go over some stuff, you have to realize the limitations. If I make the problem very complicated, then you will not be able to use these formulas easily. Okay, we are talking about very simple cases. We are usually talking about cases in which you have thin cylindrical pressure vessels that are sitting in the environment like this. Okay, so the question says that I have water inside this tank. The height of the water is 15.5 meter. So height of the water is 15.5 meter. The water is full till here. Somebody is asking me, find the sigma 1 right at the bottom of this container, somewhere exactly here. So this is the question today. They want me to give them a sigma. So I will give them sigma how? Number 1, I will say that sigma 1 is equal to PR over T for a thin cylindrical pressure vessel. What is sigma 2? Sigma 1 was hoop stress. What was sigma 2? Longitudinal. Mirich, sigma 2 is longitudinal and sigma 1 is hoop or circumferential stress. I am intentionally using this English again and again because I also want you to remember this. So what is the value of P? It is equal to G times H, again fluid mechanics comes to your rescue. It is water, 998 kilogram per meter cube or whatever. G value is 9.81 meter per second square. Hang on, you haven't taken fluids, right? Fluid mechanics? No. Oh, that's fine. Density of water, G is, again, it's a static pressure formula they will teach you in fluid mechanics. So for example, very easy, it's a hydrostatic pressure formula. If I have water till here and I'm swimming here, so it's rho gh water on top of me. If I keep on going deeper and deeper and deeper inside water, rho gh, so water will keep on piling over my head. So the deeper I swim, the more hydrostatic pressure there is on my body. Anyways, something to think about. 15.5. So this will give me nice and beautiful 152 kilopascals. And please don't get worried. This pressure can be used in the formula sigma 1 equal to P multiplied by R multiplied by, what is R? 4 minus 16 by 1000. Okay, do the R by T yourself, should be greater than 10. Again, something to think about. I'm not going for R over T all the time. I forgot. 3.984 meter, I think so. PR over T. What was sigma 1? I think it was circumferential or hoop stress. Okay. PR over T. T is 0.016. So the value comes out to be 37.9 megapascal. Sigma 1 is the circumferential or hoop stress. Sigma 2 is the longitudinal or axial stress. We did not add any atmospheric pressure into it. This is the pressure that is acting on the person, right, inside the tank. So rho gh is fine. Yeah, I don't think we will. Ek minute. Sorry. It's still the gauge pressure, right? Because 1 minute. If the atmospheric pressure is also acting from top, then the absolute pressure will become 152 plus 100. But I am also only taking 152. Why? Because it's the gauge pressure. And they told me that for using these formulas, you always have to use the gauge pressure. Good. Because at the end of the day, even from the environment outside, there is atmospheric pressure acting, right? So if I have to talk about stresses, I have to talk about the gauge pressure that is sitting inside. So everything is fine, I suppose. You can actually write here exposed to atmosphere if you're getting confused. Right here exposed to environment. So the lid is open, life is beautiful.
We assume that this cylinder, which full of water, sits on the ground. We know that the atmosphere is going to apply pressure from the backside, but not from the ground.
Right. It is like sitting here, like here.
Let's think like
this. Okay.
Atmosphere is putting pressure from here,
but
from the ground there is atmosphere does not put pressure. So can we say that like while we are taking the longitudinal stress, we should apply the atmosphere, but while we are taking the axial circumferential, like this. So while we are taking the longitudinal, we take the atmosphere, but when we take the circumferential, we.
No. Actually, I will tell you where the confusion is starting. You have to go through the derivation. So, for example, if you have pressure inside a can, that pressure is like this. It is acting like outside. It is acting like this. So the pressure is acting in all directions, right? That's the beauty of it. So if I have a can inside, there is a pressure. Pressure is acting outside arrows. Pressure is acting like this. Pressure is acting in all directions. So that's why you have to use the gauge pressure anyways. Are you getting my point? The pressure is not biased in any direction. So it will be in all directions. Gentlemen, is this clear? That's one more topic to prepare, but I think you will do fine. Just remember that in an exam setting, you have to go through all those files that I keep sending you. Remember that in thin pressure vessel, it's already present on O2 class. If you open it in an exam, I'm not going to ask you a problem as simple as find sigma 1 and sigma 2. Come on, like it's PR over T. I know everyone can do it, but I will make it a little tricky. So for example, go through those files on O2 class. I will put a line over here like this. I will say that this container is welded, and the weld angle is 15 degree. I will say if the container is welded, tell me the kind of stresses that this weld is subjected to. So what will you do? Sigma 1 is with you, sigma 2 is with you. You have to go through stress transformation equations or Mohr circle. You get my point? So now you will have stress 1, call it as, I don't know, stress X or stress Y, I don't remember. Stress 2, you will call it as another stress X or Y, whatever. You will also say, what are the shear stresses? I think they are 0 when you have principal values like these. And then you will find the stresses on that weld. So go through O2 class file. Okay. I'm not going to go that here. I think you have sufficient background to open O2 class, open those problems and do it. Hanji.
Could we draw the segment?
The one I covered last time?
No, John. In that question, for example, we find sigma 1. So when we draw it, the segment all to the surface of the tin. So sigma 1, which direction, and sigma 2 will be which direction?
I have to open the derivation that I went over. So I probably can give a try if you want.
No, John.
Ek minute. I understand. Mehmet, I understand. You are asking me to tell you the stresses. I am about to make them for you. Oh, let me use the same color actually. I understand the question. Your point is how to make them physical. Okay. So make them. Okay, now I will make. So there will be stresses like this. Yeah. Along the wall. And if this is the container, what happened? Arey yaar, this is just bizarre. This changes. It's also being recorded when I'm giving my expressions. Hang on. Come on, escape. Then I will make. I don't know now that side or this side, but just 90 degrees. So I'm just trying to tell you. I think this is sigma 2. Sigma 1. I think so. Okay, what is the question now?
So, for example,
Please.
If we draw a square segment,
Yeah, you can.
so sigma 2 will be in longitudinal, and sigma 1 will be in the horizontal. Right?
You answered the question. Yeah.
Okay.
Good.
So
Good
because,
observation.
For example, in exam, you ask a question about the principal stress at the valid plane. So we need to turn.
One minute. Say that again. I asked the question regarding. I asked the question regarding making the stresses on the principal plane. No. I asked the question regarding the stresses on the weld. Sorry, on the weld.
So we need to use these values and also the angle. So we
Good.
try to twist. Yeah.
Good. But I stopped you there because you said you are going to ask us about principal. These are already principal stresses, by the way. Like if I say stress 1 and stress 2 and there is no shear here, I'm talking about that these are themselves in their origin, in their totality, in their intrinsic sense, they are They are principal stresses actually.
If you don't mind, can you repeat the question again about the
Okay, will it be fine if I answer that in the last 2-3 minutes?
You said it's all over the class. What kind of
O2 class, just open the O2 class, latest weekly files. On that, I have posted a lot of files. You will open, there are some questions regarding thin pressure vessels. When you double click on that, there is a thin pressure vessel question, but PR over T and PR over 2T, it doesn't end there. It has a weld over it. It says if I am trying to weld the container.
Pressure vessels, practice problems.
Good. Thank you, Usman. So thin pressure vessel practice problem, O2 class, open it. You have to go through those problems. Did I answer your question? Okay. Okay, gentlemen. I hope it's not confusing, although it's one more topic to worry about, but I'm trying my best that it's clear.
I would like to repeat my question again.
Yeah, please.
Even though the pressure acts on the all surfaces, at the bottom, at the G2, the air pressure does not exist in the bottom.
You know, Ahmed, let me tell you something. Even if this object is sitting on the floor, what happens is that we are not talking about that we have completely sealed it. If you are placing something like this, and if you are not sealing
I understand.
So
there is air, so there is air pressure.
yeah, it's and on top of that, like come on, like even in a hypothetical sense, if I agree with you, are we really sealing a cylinder on the bottom and making sure that there is no air? Oh, come on, we have a cylinder that is like this. We put it on the bottom. So for us, it is exposed from atmosphere from all ends. So don't worry about that. I could even if we stick to this point, we will go around this. For example, in my way, that the cylinder in any case is very long. So really, are we gonna bother about taking care of that? Another thing that you have to realize is that these are rough estimations at the end of the day. Like they always give you ballpark figures. So for a thin pressure vessel, they will just give me an idea about the stresses. If I have to really design a cylinder, I will have a ballpark figure, but then I will put it through rigorous ANSYS or those kind of tests. So these are very ballpark rough figures that I get. But yeah, these are the couple of ways I'm trying to answer the question. Okay, gentlemen, on that note, I would take the opportunity to take this to the next level. So I really want you to be with me on this. We will go slowly, but remember that the portion where I want you to focus, that will be the exam. This is how I will ask the question in the exam. So it's very easy. Don't worry that it's a new topic we are covering. Relax. Last semester, students went over it. You will also go through it. So just understand the problem statement first. And then I will also relate this to a physical problem, because what you are seeing on your screen is not physical, right? What we are talking about is columns right now. So what's the deal with the column? I'm talking about that there is an object that is subjected to a load in the axial direction. What my focus today is, very quickly in the next 25 minutes, we will talk about the elastic stability. Okay, one more thing to think about. What is the meaning of elastic stability? So if you have even a basic ruler, think like that, and then we will talk about practical problems, and you are subjecting it to a axial load, you keep on putting more and more load onto it, right? Now we have this observation that ruler will, it will buckle. It will definitely buckle. All of us know it. Good. Now, if I have to ask you, when would this ruler fail, right? When will it fail? Let's say your focus will be that it buckles. Now, if you put more load, let's say, it will not come back. So we will be thinking about buckling all the time, right? Now, let's change the problem and let's talk about not steel ruler. Now let's talk about this board marker, right? Again, I will put a load on top of it. Now, I doubt that any one of us really would love to think about buckling, right? Because we have this intuitive feel that if it has to fail, probably it will just, what do you call? It will fail under yielding, right? So if I have a thin structure that is very long, it tends to fail by buckling. If I have a short structure that has a big dia, let's say, it tends to, what was that English word for it? It would fail under yielding. That's correct English. But I think let's stick to fail under yielding. You get the point. Thin, long would fail under buckling. Very short would fail under yielding. So this is the problem in our hand. Now I have created that big structure on the left. What you have to understand is that in a practical problem, you will have a genuine long structure. It will have a stiffness to it, right? And you remember that stiffness with the word K. You remember that K? That is the stiffness. Now, what I have done is I have created this hypothetical problem right on the left. I have said, let's say we have this thin rod, and I take out the stiffness out of it, and I use a torsional spring to model the. Yes, you get it. This is a very theoretical construct. In a practical life, in my steel ruler, I don't have a torsional spring. I have a stiffness that is given by that ruler. But this is a hypothetical construct from my side. Now what I'm doing is I'm putting a load from the top. Please bear with me. What will happen? This object, I keep on putting more and more load. At a point, you can see, in fact, not more and more load. Even if I give a little load, you can see that there is a roller. The object goes down, and you can see that this bends, and this torsional spring is providing a counter moment. So the restoring moment is given as k theta multiplied by 2 theta. K theta I will be using as beta in this whole class. And at the end of the day, I am making a free body diagram. This is a pin joint. There is a roller, and there is a torsional spring. So this is how we will proceed in this class. The problems will be very interesting, by the way. So far, so good, right? Nothing fancy till now.
What is K theta or beta?
K theta is the beta. Okay, got it. Good question. So should I write it here instead of? I also write everything there. So you see, you remember this F equal to Kx, right? Okay, instead of F, write M. Instead of K, write K theta. Instead of X, write theta. Got it? Is this even visible here? Wow, this camera is very good. So far, so good, gentlemen. Okay, life is good. Just bear with me, okay? Okay, here comes the new concept. I could not explain that because I did not know. I have written something very important here. So let me put it here. And now let me explain to you the next concept. Okay, now what I will talk about is stable and unstable. So bear with me. I put a load. The thing goes like ting. The moment I remove the load, this thing will go straight again. Good. I do it one more time. Now I apply a greater load. Ting, right? And then I remove it. Again, it goes back. Good. Then I put greater load. It again does tin. But this time around, I remove the load. It doesn't go back. So now you have to understand two different situations. I put a critical value of load. As long as I am less than that load, the object will, the column will keep on coming back. Good, stable system. I put such a huge value of load that when that buckling has happened, even I remove the load, the object doesn't want to come back. So remember the value, the understanding of critical load. Critical load is that virtual boundary. As long as I am less than that, I keep on applying load, it keep on doing like ding, and I keep on removing it. Object keeps on coming back to its straight shape. Great. I am applying a load less than the critical value of load. Exactly at critical value of load, the object is having its hands up. It's saying, you know what? You give me a little more load than this one. I'm not going to come back. I'm going to fail. So you put a little more value than that. It remains like that for the rest of its life. It has failed, doesn't want to come back. Yes.
Hocam, so stable is plastic deformation, unstable is the
No, when did I say that?
elastic, and but when you're talking about buckling idea,
Ah,
so for example,
you mean unstable is plastic?
stable is one the elastic, unstable one is the plastic.
Oh, got it.
deformation.
Yeah. So I will use the word permanent deformation, that it has gone, doesn't want to come back. Yeah, you can call it like that. I will avoid using those words because plastic deformation and all of that stuff is actually not in our class. So that's why I don't want to comment. But yeah, you are getting the feel of it, that as long as you are less than the critical load, it buckles, but it comes back. Greater than critical load, it's unstable, doesn't want to come back. Is it clear? Should I proceed now? Good. We will do it. That's what is coming in exam. Now let's talk about the next one. I do realize that you are like, why are you showing all of this? You usually write it on hand, because these are some pretty simple derivations. That's why I'm sparing some time. Now what I am doing is I take that little object, cut it. So I have a load P that is acting. There is a theta angle. When I cut it, I have a moment and a P that is acting like this. I do the summation of moments. So it is equal to beta multiplied by 2 theta. And I know that instead of using as M is nothing more than P L theta by 2. So finally, I equate them and I get a very simple. Hang on, I think students are also writing. So I need to, I will just adjust it so our students can write. Hang on, let me put it like this. So I equate it like this and I get the value of critical load as 4 beta by L. So again, it's just, I cut it. I do the summation of moments. The beta 2 theta is this one. Hang on, everyone, this one. K theta is beta, right? The restoring moment that is provided by the torsional spring. If you are really confused what is happening like this, let me put it like this. You apply the load, right? It buckles. You remove the load, it comes back. Why? Because the restoring moment given by the torsional spring was good. It kept on bringing the object back. But the critical value is that the torsional spring has had it. It's like I'm done with it. So you just equate the maximum countering moment that or the restoring moment that torsional spring can provide. You equate it with the maximum load that you're putting it to, and you get the value of critical load as 4 beta by L. Now I will start writing as I always do. Is it clear how did we find critical load? Yes, no?
What is CR? PCR?
CR, critical. No? Okay, our students are like, why are we doing this? Okay. By the way, this is not the end of it. Actual derivation is there. Yes, please.
Beta is related to material.
Good.
And
Good. Beta is related to
how
material.
come we can calculate beta without without using the Young rules?
Good. Very good. I'm not sure how did you arrive at it so quickly, but this is what we are going to do the next slide. Very nice. Beta is the elastic modulus. You have to understand that this is nothing actually. I'm not going to ask you this in exam. I'm just telling you that I have modeled it with a k theta, and this is what the critical load is. It's just a very basic derivation. It has no, there is no significance in terms of exam. Now I will answer Ahmed's question. Let's do it together. Good remark, Ahmed. So his question is, how can we talk about the restoring the torsional stiffness without talking about the elastic modulus? I will answer his question like this. Again, I'm talking about the roller. You apply a very little load, the object, what will it do? It will buckle, right? Because you have a roller. You have a roller, right? If you have a roller, what does a roller do? Nothing. Roller cannot support in the y direction. You put a very little load. What will this object do? It will buckle, right? Even with a little load. You put more load, it will buckle more. You put more load, it will buckle more. You keep on putting more and more load, it will keep on buckling more and more. And at a critical value, the object has had it, it will not be returning back to its straight form. So now I will answer Ahmed's question. Good. So why don't you tell me the x-axis is along this, the y-axis is perpendicular to this. I will write plus py plus m equal to 0. Agreed? What will be my moment, by the way? It will be equal to negative py. Agreed? So now I will ask you, what is the formula of moment? And Mirj, can you help us? There was this moment formula that we studied in beam deflection. M is equal to EI. Now look at your notes. There was some formula that we studied in beam deflection. M equal to EI. Good.
Second derivative of d over d.
Very good. I already remember, but I really want you to look at your notes. D square V. What is V? Deflection. Okay, is equal to, you see, now Ahmed's question is also answered. How can we talk about everything without elastic modulus? So you see, suddenly, now you can look at like this. This EI D square V by dx square is giving you that restoring moment, right? I am applying a load py, more py, and every time EI d square V by dx square is countering that, it keeps on taking the system back. So E appeared. Very nice. Now what I will do is EI d square V over dx square. Just bear with me, please. Py equal to 0. I have to go through these little derivations, otherwise. So last but not, okay, I think I have used y here. Please forgive me. So let me use instead of vy. We were using v right before. That's fine. I think nothing will happen if I take the liberty of using y here, because I have using y here. So y is for deflection, at least in this topic. Bear with me. So d square v, as one of the students said, divided by dx square plus p over ei. So you don't need to worry. I will not go into too many derivations. Okay. Now, what is lambda square? It is equal to p over ei. Have you solved such kind of equations in your ODE classes? I think you have. Ordinary differential equation professors have been teaching you all of this. Does it ring bells? So now, I think we have 9 minutes. We are good to go. In 9 minutes, I will be able to finish this. So take your time. We haven't started any example problem. Next time, definitely, we will have P over EI. Lambda square is P over EI. In ordinary differential equations, they told us these techniques. I am intentionally using a lambda or lambda square for my own benefit. I want to solve this using my hand. I want to solve this differential equations. If you don't like to name it with lambda square, that's fine. In any case, you will have to take it as a constant in this particular problem and solve it. I want to, hang on, I want to solve y, the deflection. Yes.
Lambda is the eigenvalue, right?
It should be, is it? I don't know. Yeah, some x1 dot equal to x2, probably lambda or lambda square. You are very close, yeah.
Hocam, also I have a question about the moments direction. For example, we cut it at the middle or somewhere.
I look from here, I cut it from the right, I throw that portion and I put an anti-clockwise moment.
I understand like this. We cut it like this.
G.
Right?
G.
And you said that P is acting like this, and the moment acting like this. So how can we decide that the moment acting like this?
Yeah, that's what I'm saying. I looked at like this. I cut it, I throw the right chunk away, and I saw my statics classes. They told me when I cut from the right, I put an anti-clockwise moment. Okay. No? Does it ring bells? Well, in statics, that's what they told me, right? I used to cut, I used to throw the right chunk away. Okay, gentlemen, we have to go through this derivation. Please bear with me. I know derivations are sometimes hard, but I will not be able to solve any examples with you if we don't go through any background. So now, again, ODE 45 stuff, I mean ordinary differential equation stuff. Y is equal to e power mx, right? Does it ring bells? Then you put m square. Mirch, you remember that from everyone? Does it? Do you remember from your differential equations that you used to model this like this? Okay, m square plus lambda square into e power mx equal to 0, right? So our professors used to tell us that the roots of the characteristic equations are like this. And then when I used to ask them, what is the meaning of this? They used to say, it is sine of lambda x. By the way, this derivation is not coming in exam, but is it clear? No? Yes. I am solving the second order differential equation. Okay. Okay. No worries. Now, what was lambda? Lambda square is P over EI. Can anyone tell me what is I?
First moment, not first moment. The
Moment of, the area moment of inertia. I also remember like that. Okay. So, quick question. Can anyone tell me how to find C1 and C2?
by using boundary conditions.
Right? Good. Very nice. Quick remark from both the students. So I think if you look at the boundary conditions, then y is 0 for both the fellows, right? Y is 0, right, everyone?
Y
Yes.
is 0 at A, but not at B.
Why?
Yeah.
That is a roller. Roller can allow it to go like this, but y at B is also 0. Good. I hope this is clear to our students. Again, derivation I have to go through. So y at 0 is equal to 0. So I get C2 equal to anyone? 0, right? I think so. Okay. And then y at L equal to 0. So I will get 0 equal to C1 sine of lambda L. Please bear with me. I understand the derivations can become lengthy. And C2 cosine of lambda L. Oh, sorry. Yeah, my mistake. So now I have got C2 is 0. So I will get 0 is equal to, as Ahmed said, C1 sine lambda L. So what will be? C1 is not equal to 0. No, if I put C1 as 0, I will get a trivial solution. I want non-trivial solution. Have you heard of this word from your previous professors? I'm not sure how much you understand this, but trivial and non-trivial means that, like, what is the solution? What is the dynamic solution of this remote? Well, 0. Sitting here, right? 0. Unless I give it an initial condition, I will not have a non-trivial solution. So we want non-trivial solutions in our life. So C1 is not equal to 0. Nee, ek minute. What did I say? Yeah, C1 is not equal to 0. So sine lambda L equal to 0. Mirj has a question. Mirj has a question? Mirj, ask me. What happened?
Hocam, I can understand in the yellow part.
Y is at 0 is 0 and C2 becomes 0.
Yes, 0, but in the green part, I don't understand. How can we omit the constant?
Because C2 is 0.
I need to balance.
C2 is 0, na? So I put C2 equal to 0 here. Because one of those, okay. Acha. So any student who can tell me what is the value of lambda then? Sine inverse 0. So what is sine inverse 0? Sine inverse 0 is 0. 0 and pi, right? So I will get n pi, correct? So lambda will be n pi by L. Oh, come on. I know everyone is saying, what are you trying to do? So what will be lambda square? It will be n square pi square over L square. So what is the value of P critical? Just bear with me. You have really followed everything. I will say lambda square is P over EI. So P over EI is equal to n square. Instead of this, I will put CR. N square pi square over L square. And P critical comes out to be n square pi square over L square into EI. Okay, let me write it in a nice, beautiful orange color. I know it is so confusing, but this is what I want all of you to remember. P critical is equal to n square pi square over L square into EI.
Hocam, do we need to know the derivation?
No,
Are we responsible for the derivation?
No.
Can we just use the-
no. This derivation is not coming in exam. This is too much for you guys. Okay, next time, 2 hours, all we will be doing is we will be solving some examples. Now, I really don't want to leave it at this point. I will take 2 minutes because I really want you to connect the dots. Please bear with me. These are the 2 minutes that I was trying to take you to. So as much as you have been patient, please remain with me a couple of minutes more. Yeah, we are here, right? P critical, we got it, right? Okay. Now, these are the 4 cases. This is not an advanced class. I'm skipping the derivations. For the 434 guys, we went through this crazy derivations. Now we will have 4 cases. 4 cases, we will have 4 cases. In all the 4 cases, I will have an object and it will be, I will be able to apply load on it. First case will be hinged. Second case. Now, don't think that this object still will have load on it. Okay, don't think that I fixed it like putting it inside something. It is fixed. This, for example, when I use the word fixed in the sense that this portion is fixed, this is hinged. When you look at fixed, you see this end can still move. So it is not fixed like putting lines here, because putting lines means that this fellow cannot go down. But fixed here means that this object is inside this, but this fellow can still move down. I have 4 cases. I hope I have explained. Hinged, fixed, free, fixed, hinged, fixed. I told you the formula. It is pi square EI, whatever that formula was, I forgot. So pi square EI over L square. For these 4 cases, it will be pi square EI over L square, pi square EI over 4L square, 2 pi square EI over L square, and 4 pi square EI over L square. So in an exam setting, you will be using these 4 cases. I will be providing you the 4 formulas. You will identify whether it's a hinged case, whether it's a fixed free case, whether it's a fixed hinged case, whether it's a fixed case. That's your responsibility. We will go through some examples. Then I change this formula. P critical is equal to pi square EI over LE square, where LE is the effective length. For the hinged case, effective length is L. For the fixed free case, effective length is 2L. For the fixed hinged case, effective length is 0.7L. For the fixed case, effective length is 0.5L. So in an exam, you will see the formula pi square EI over LE square is equal to PCR. What is LE, effective length? You will identify the case. If the case is fixed, effective length is 0.5L. You write 0.5 multiplied by L instead of effective length. If it's a fixed hinged case, which we will talk about those cases, don't worry, you will say effective length is 0.7L. Similarly, effective length equal to 2L. Similarly, effective length equal to L. And next time I will do problems. So remember, P critical is equal to I'm about to say bye bye to you. Pi square EI over LE square. So just remember this. P critical is equal to pi square EI over LE square. Pi is 3.14. E is the elastic modulus. I is the area moment of inertia, and LE is the effective length. That for all those four cases is
So all on the other equations of critical load.
huh?
L's in the critical load equation.
Yes.
Those are all LE.
LE. So
LE.
these are L's.
These are L's.
You can see na, divided by L square, divided by 4 L square, divided by S square, 4 pi. But it's easy to remember this one, right? But one formula, P critical is equal to pi square EI over LE square, where LE is different for all the four cases. So you remember only this.
One equation.
And then in an exam, you know that if LE is L, then you get this formula. If LE is 2L, you get this formula. If LE is 0.7 L and you substitute here, you get this formula, because I think you get my point, Ahmed. If you put LE equal to 0.5, you will immediately get this. So just remember this. Pi square P critical load is equal to pi square EI over L square. One more minute and I will say goodbye. Just one more comment. There are students who are saying you use the word N here, right? Where is the N? This one. Yeah, this one. But I never showed you any N. N I had to put 1, because if I'm talking about the minimum critical load, I have to put N equal to 1. What happens at 2, 3, 4? Those are advanced topics, but next time I can just briefly on whiteboard tell you what will happen when N is 2, 3, 4. That's not our concern. Thank you. And thin pressure vessel, I told you what you have to prepare. Elastic stability of columns, we are going through it. Next class, don't skip the next class. That's my advice to you. Let's go to dynamics for those of you who are taking that class with me. Bye-bye. And you can have actually a 10-minute break. So for example, you can come at 11:45 if you want, okay? Okay, did I have to? Oh, Hasung came. Hasung, did you understand everything? Any questions? Hasung?